Morning, everybody. It's Friday. As promised, I told you I was going to hit you with a video today. I'm at home with a laptop that has a touchscreen and a digital pen that does a good job drawing. I'm going to cover two things in this video. It's a way to get more familiar with just common values you'll see when working with a unit circle. And then I'm going to talk about simplifying radicals and fractions with radicals. And before I do that, let me just bring something up. This week you had the conversations going on where you did a post about yourself and your thoughts on the beautiful trigonometry video. I don't think I was clear enough about how that was scored. Just so you know, it was 7 points for your post and then 3 points for 3 replies. So for those of you who are still working on that or used a late pass, just you'll get a point for every reply you do, and then 7 points for the initial post, but you only need to reply to 3. So that'll stop at 10 points, you'll notice. Okay, let's look at the Word document I have open. So like I said, this is a way to get familiar with some of the, let me make sure I'm sharing the right thing. Nope, I'm not. In fact, there we go. To get familiar with these values. So I'll tell you what I thought of this is at one point it was asking about 5 pi over 3. And I just realized, like, when I think of 5 pi over 3, my mind doesn't immediately jump to where is that on this circle? Well, I know 5 pi over 3 is more than 1, so I know it's more than 180 degrees, but beyond that, I'm not sure where. So I'm going to give you a way to help, and this is maybe counter to intuitive to some of you because we're so used to being told to simplify fractions. But I think part of the reason these numbers look so unfamiliar is because everything's simplified. And I wanted to make sure you understand another way to think of it. So first thing I'm going to do is divide this just into the 30, 60, 90 degree angles. And you'll notice that essentially if we think of this full length of 180 degrees or pi, then you can see that this 30 degree, when we split into 30 degree angles, 30, 60, 90, 120, 150, 180, that's made a perfect division of 6. So if you look at the whole circle, you can think of it, a lot of pizzas come cut into 12 slices. So it's like slicing that. So for as far as radians go, it's kind of helpful to think of this as 1 pi over 6, and that's exactly as it appears in the other things you've seen, 2 pi over 6. And then if you look at this, that will usually be called pi over 3, and that's because 2, 6 would simplify to 1/3. But in a way, it's kind of easier to think of this as, oh, this is just 2 of those, right? And even though this is usually written as pi over 2, if you think of that as 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, which of course equals 1 pi. 6 divided by 6 is 1. 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6. And I'm not even going to write this last one. 12 pi over 6 gets us back to the start. That's equal to 2 pi. If you do 12 divided by 6 is 2. But again, the reason I do this is because if you think of this as all these angles are broken into sixths, if you ignore those 45-degree ones, then it's just counting by sixths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sixths. And for me, that would help me be like, oh, right here, 10 sixths is the same as 5/3. So there's my 5/3 angle that I couldn't immediately think of. Okay. You'll notice we kind of skipped over some of the angles, and that's part of the reason I think why this gets confusing is, they're not equally spaced. It jumps by 30, then jumps by 15, then jumps by 15, then jumps by 30. But if you instead think of it as, okay, another way we could divide the circle up is to split it into 8 parts, whereas we take the 180 degrees and say, oh, well, if we divide that by 4, larger slices of pizza, then we would say this is really just 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, which again also equals 1, just like 6 pi over 6 equals 1. But and then just think of it as a separate, so if you start by just thinking, are we talking about 45-degree angles or are we talking about 30-degree angles? That separates whether that pi is divided into 4 parts or 6 parts. And then continuing this just to wrap it up, 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4 would be the same as 2 pi. So again, maybe some of you don't need this. Maybe you've already memorized all those values. But to me, when I look at this, the numbers seem less random. And there's a little more order to it and a way to think through that rotation of the circle, which is always a good practice to just always work in that counterclockwise motion, except remembering that if the angle is negative, then you're moving in the clockwise motion. Okay, and this one you might have seen if you watch those slideshows, which I recommended you do. Steve Kangas pointed out this other thing that these XY values here, which seem, again, maybe kind of like, oh, 1/2 and then square root of 2 over 2 and then square root of 3 over 2, might seem kind of random. There's a nice way to think of those numbers, and I'm just going to zoom in a little more just so I can write bigger, and I'm just going to focus on this first quadrant here. Notice that this, starting with the y values, which if we count up moving in the counterclockwise direction, if we think of that 0 as the square root of 0 over 2, and then we think of this as the square root of 1 over 2. Notice the square root of 0 is just 0, and 0 divided by 2 is 0. So that does give us back that 0. Square root of 1 is 1. And if we took that square root, it would work out to be 1/2. The square root of 2 over 2, the square root of 3 over 2, and the square root of 4 over 2. Notice that those give us, these two are exactly what you'll see in your unit circle, square root of 2 over 2 and square root of 3 over 2. Square root of 4 over 2, square root of 4 is 2. 2 divided by 2 is 1. So it turns out that this y value is 1 right here. And then if we pick up right here at the square root of 4 over 2 and start with the square root of 0 over 2 for the x value, when x is 0 right here, and do the same thing but working backwards. Notice that that gives us back the correct values in the x coordinate as well. So again, my goal here, I think I might have shifted that drawing a little bit just by, yeah. My goal here was just to being familiar with these angles and coordinates as a big start of just speeding your game up and being able to recognize things very quickly. And for me, it helps to break that down a little bit instead of just seeming a random collection of numbers because of simplified fractions. If you want to, you could have a version of this that has these unsimplified fractions that really show more the counting up as you go around. I'm not going to go over the rest of coordinates because they're all follow the same pattern. As the y variable moves down, in this case, it would go back to the square root of 3 over 2, back to the square root of 2 over 2. And you can even see that anyway because they're across from each other so that they're the exact same height or the same y variable. And we've already played with that a little bit. I have one more thing I want to talk about that video, and just there's not really any formal instruction in here about simplifying radicals. It sort of assumes you've done that recently. So I'm going to look at, say, the square root of 2 over 2. I'm sorry, that's simplified. So once you start looking at, well, let's look at this. So the cosine of pi over 4, assuming it's the unit circle, is going to be square root of 2 over 2. Something you're introduced to in 5.4, which comes up next week, is that there are inverse functions, and essentially the secant function is the inverse of the cosine function. So secant of pi over 4 is equal to 1 divided by the cosine of pi over 4. And in this case, it would be 1 divided by the square root of 2 over 2, right? Okay. So if this was a question on WAMAP and it says, what's the secant of pi over 4? And your answer was 1 divided by square root of 2 over 2, and you type that into WAMAP, it would accept it as the correct answer. But if you got it wrong, here, let me erase this. But if you got it wrong and displayed the answer, this would not show as the answer because this is not a simplified fraction. So what I'm going to do now is just say if we wanted to simplify 1 over the square root of 2 over 2, there are several things going on that makes this not simplified. One, if we consider this 1 the numerator and this whole fraction the bottom of the denominator, it's inappropriate to have a fraction within a fraction, or to have a fraction in the denominator that would say don't do that. So a first step on this would say, okay, well, if I multiply top and bottom of this fraction by 2, that solves that problem of saying, well, we can get rid of the denominator within the denominator by multiplying top and bottom by 2. And this gives us 2 divided by the square root of 2. Now that's a little better. It's no longer a fraction with a fraction, but it still isn't fully simplified because a fully simplified fraction does not have any radicals in the denominator. And what that square root of 2 in the denominator would be a radical within the denominator. So to get rid of that, essentially, if you want to get rid of a square root, you would square it. But we can't just square the top and bottom because these aren't equal quantities. It's not like squaring both sides of an equation where we know both sides are equal. But we can say squaring that square root of 2 would just mean multiply it by itself. And we can multiply by the square root of 2 on the bottom as long as we multiply by the square root of 2 on the top. And what that gives us is, on the bottom, that square root of 2 times square root of 2 just gives us 2. And on the top, we have 2 times the square root of 2. All right. We don't have a fraction within a fraction. We don't have a radical inside the denominator. But there's still one more problem with this that stops it from being fully simplified. And just to add on this, I think of simplification as setting the table right, right? 1 divided by square root of 2 over 2, the original fraction we're working with, is a mathematical amount that equals a certain decimal. And all these things we're getting to are still equal to that number. But the simplification process is agreeing that when a number appears in its final form, that this is how it looks. So it's kind of like good etiquette mathematically. So then the last thing we have is just another element of simplification is if there's any repeated factors in the top and bottom that can reduce, you would reduce. So the last step of this is say, oh, both of these have a multiplication of 2 in them, so that would reduce. And the final answer would just be the square root of 2. And so if you were in WAMAP and you answered the wrong thing and it looked kind of like this top fraction, 1 over square root of 2 over 2, and it tells you you're wrong, and you look at the right answer and it says square root of 2, you might think, I wasn't even close. But the reality is it might just be simplification can make the numbers look quite different than when they started. And I think we can all agree that the square root of 2 is much simpler than 1 divided by the square root of 2 over 2. So anyway, simplification, it might have been a while. In my opinion, this is the most difficult simplification of a radical and a fraction that you have to do in this early part. So I modeled that for you. Anyway, I hope you have a wonderful weekend. I hope you use Martin Luther King's birthday to do some action. There's great stuff at Garfield High School. There are marches, and I won't be there today because I'm going to an all-day event around the birthday at South Seattle College. So all the best to you, and I hope to hear from you soon, especially if you're needing any help or support. All right, take care.